Welcome to Tutorial 5 using automatic controllers in GPSX. To best follow along with this tutorial content, please complete tutorials 1 and 2 prior to attempting this tutorial. Automatic process control is widely used in the wastewater treatment industry. Controllers are commonly implemented to control the MLSS concentration and dissolved oxygen in the aeration basin. The objectives of this tutorial are to learn how to set up a dissolved oxygen controller that changes the aeration rate to meet a DO set point, and to learn how to set up an MLSS controller to adjust the biosolids wastage rate to meet the MLSS set point. Having good control of these variables allows for improvement and stabilization of operations, as well as allowing for energy savings. Open your Tutorial 1 model layout. If you did not complete Tutorial 1, you can do so at this time or select the model layout from File, Sample Layouts, Tutorial 1. Save the model layout by a different name in an appropriate directory. By default, the aeration tank is set up to use a DO controller, but we will just double check. Within the simulation mode for the aeration tank, go to Input Parameters, Operational, and in the Aeration Setup section, the Specify Oxygen Transfer by Variable should be set to using a DO controller. If it isn't, switch into modeling mode, change the value, and come back into simulation mode. We will now create input controllers for the DO set point. The set points can be accessed from the aeration tank's Input Parameters Operational form under the Aeration Control section. Click on the ellipse button beside the DO set point label to access the individual array elements. Drag the first and last DO set point array elements to the Input Control tab to create the sliders. The range of 0 to 10 mg per liter is appropriate, so we will not make any changes to the input control properties for this variable. Rename the tab to DO set points. We will now create an output graph containing the dissolved oxygen concentration in the first and fourth reactors, as well as the effluent ammonia and nitrogen. Right-click on the aeration tank and select the output variables, state variables, and individual reactors. Beside the dissolved oxygen and reactors label, click the ellipse button to access the individual array elements. Drag the first and last elements to a new graph. Right-click on the aeration tank's effluent stream, not the tank itself, and select Output Variables, State Variables, and drag ammonia and nitrogen under the nitrogen compound section to the graph. Edit the graph settings, rename to Dissolved Oxygen and Ammonia, and change the max value of the y-axis to 10, which is the same as the DO set point slider limit. Auto-arrange the graphs. Save the layout. Run a 20-day simulation varying the influent flow rate and DO set points. We are now going to add an MLSS controller to the layout to automatically adjust the biosolids wastage rate to meet the specified MLSS set point. Switch into modeling mode. Right-click on the aeration tank's effluent stream and select Output Variables, Composite Variables. Right-click on the label for Mixed Liquor Suspended Solids and select Copy Cryptic Name to Clipboard. This will store XMLSS on your computer's clipboard so you can paste it into a field later. Right-click on the clarifier object and go to Input Parameters, Operational. Within the Pump Flow section, turn on the controller and put the set point for the control variable to 2000. Replace blank with XMLSS in the control variable field. Use Ctrl V to paste the cryptic name if you had previously saved it to the clipboard. Enter 0.05 days as the controller sampling time. This represents the frequency with which the controller samples the control variable, or MLSS in this case. Turn off the controller effect on control variable direct. This means the manipulated variable, the wastage flow rate, is increased to reduce the control variable MLSS. A different control loop, such as the airflow and DO concentration, would require the controller effect on control variable direct switch to be turned on, as an increase in the manipulated variable air would result in an increase to the control variable DO. Enter 200 m3 per day as maximum pump flow. Accept this form and save the model layout. Switch into simulation mode. We will now create a set of 5 new input controls for the MLSS. Right-click on the clarifier and go to Input Parameters Operational. To the input control area, drag the controller on-off switch in the set point for the control variable. In the pump flow more form, drag into the input control area the proportional gain, integral time, and the derivative time. These are all components of a PID type controller. Rename it to MLSS Controls. Click on the Controller's Property button and make adjustments to the maximum and minimum values. Right-click on the aeration tank's effluent stream and navigate to Output Variables, Composite Variables, and drag the Mixed Liquor Suspended Solids variable to a new graph. Right-click on the influent object and go to Output Variables, Flow, and drag the influent flow to the same graph. Right-click on the clarifier's pump stream and drag the wastage flow to the same graph. In the Graph Properties window, rename the graph to Influent Flow, MLSS, and Wastage Flow. And change the maximum values to 5,000, 5,000, and 600 for the influent flow, MLSS, and wastage flow respectively. Ensure that the fields are unlocked when making this change so that the values can be edited individually. Auto-arrange the graphs. Create a new scenario and name it sinusoidal. Within this scenario, change the influent flow type to sinusoidal by right-clicking on the influent object and navigating to Flow, Flow Data. Save the model layout. Run a 10-day simulation with the controller turned on. The simulation provides the basis for tuning our MLSS controller. Notice that in the output graph, the wastage rate oscillates widely between the maximum and minimum values. This indicates an issue with the controller tuning. We will now explore adjustments to the controls to create a more stable response. Change the proportional gain to 0.001, the integral time to 10 days, and the derivative time to 0 days. Rerun the simulation and observe the effect of these changes. You should see that the controller settings result in a sluggish but stable response. Rerun the simulation, but this time increase the flow rate. This flow rate acts as a disturbance to the system. If the wastage rate does not respond quickly enough, increase the proportional gain as needed to get a reasonable and stable response. The proportional gain is responsible for adjusting the speed of the control system response. Once the proportional gain is stable, adjust the integral time to increase the controller performance, and if there's too much overshoot, try increasing the derivative time. The integral term is responsible for driving the steady state difference between the set point and process value to 0. The derivative term controls the rate of change of the errors and thus controls the amount of overshoot. Run a few more simulations adjusting these PID controller settings. Process control can be a complicated subject, and more information regarding PID control is available in the GPSX Technical Manual. Create another scenario based on the sinusoidal scenario and call it tuning. Right-click on the clarifier and go to Input Parameters, Operational, and navigate to the Pump Flow section's More form. Within this form, go to the Pump Flow Control Tuning section. In this section, turn the tuning switch on and drag this variable to the Input Control tab. Also set the fractional step size to 0.5. Accept this form, and within the operational form within the pump flow section, turn the controller off and set the pump flow value to 100 m3 per day. The 0.5 fractional step results in a step in the pump flow from 100 to 150 m3 per day. Accept this form. Now let's make sure that we have all the right settings since we made a series of many changes. In the simulation toolbar, select Scenario, Show to see all the variables that were changed within this particular scenario. Within the Input Controls section, turn on the MLSS controller and run a 0-day steady state simulation. We are doing this so that the values of the manipulated variable and controlled variables, pump flow and MLSS respectively, are representative of normal operating conditions. Now run a 10-day dynamic simulation. The output shows that the step occurs at 0.5 days and that the simulation is approaching steady state at the end of the simulation window. The PID tuning constants will be calculated once the simulation completes. Access these by opening the command window from the simulation toolbar. We will add these values to another scenario. Set the controller values to those in the command window. Turn on the MLSS controller and turn off the tuning mode. Press the Transfer Controls to Scenario button on the Controls toolbar and add the controller tuning constants to the scenario to store these settings. Run a 10-day simulation and decrease the influent flow. This will test the controller performance under dynamic conditions. As you can see in the output, the system approaches steady state towards the end of the simulation window. Save the layout. You have now completed Tutorial 5 and should be familiar with how to set up automatic controllers and adjust their tuning parameters in GPSX.